All right, in this video, we're going to be talking about predicting with an exponential best fit model. So we've done predicting with a linear best fit model, but now we're going to do it with exponential. So just like when we did linear, remember we did y1 squiggle mx1 plus b. We're going to do the same thing. It's still going to be y equals a times b raised to x. The only difference is the y is going to become a 1, the equal is going to become a squiggle, and the x up top is going to be a y1. Now, there is an additional step where you have to click the log mode. I know that you're probably not going to understand what that means right now, but you do need to click that in Desmos to make sure it comes out correct. So, how do we find the best fit model? So it's going to be very similar to what you're already used to. So using the exponential best fit, you're going to substitute the x value given to make a prediction. So whatever they ask you for, you're going to substitute that x value into the equation, and that's going to give you the y value of the prediction. Okay, so when we're doing these, again, we're looking for the x value and the y value, but we're going to be substituting in the a and the b. So the a value is always where it's at. So we have a, whatever they give us for a, and then my b value is going to be, again, whatever they give me to substitute when we substitute that in. And then, of course, we're going to substitute in the x value. So that x value, whatever number they're asking us to make a prediction, and whenever that prediction comes out to be, that's going to be the y value that we get as the output. Okay, so it says a cup of soup is left on the countertop to cool. The table below shows the temperatures in degrees of the soup recorded over a 10-minute period. What is the exponential regression equation? So whenever you see that word regression, they're talking about the best fit model. So we need to find the best fit model for this exponential. So we're going to put this in Desmos. Now I'm going to pull Desmos up and I'm going to split screen here. So hopefully everything works out correctly. Now, if we were doing a new equation, remember if we were in Desmos, we go to plus. Now I'm in the regular version. You would only have a few, and we hit table and we type in our x's and our y's. Now, to save myself some time, I've already typed those in. So I've already hit the plus sign and I've already put in my values. Now remember that if we hit this little the button on the side that looks like a magnifying glass, it'll kind of zoom it for us. Now, we could absolutely fit this linear, and it probably would still have a close linear relationship, but they asked us to find the exponential. So we're going to type y1 squiggle, and then we're going to do a times b, and then we got to make an exponent. That exponent is right there in that top corner, and we're going to type x1. Now remember what I said, in order to get the correct values, we got to click that log mode button. So if we want that log mode, we got to click that, and then it's going to give us those values. So the values that it gave us for A were 180.7 or 377, and then it gave me B, and B was 0.954. Now, if you notice, if we're looking at our R value, our correlation coefficient, so our correlation coefficient was negative 0.994. So it is going down, and it is a pretty good fit. Now, if I went back into linear and I did y1 squiggle and x1 plus b, you would notice that it does also have a good fit right here. It actually is well, they're both really close. So 0.992 and 0.994. The exponential is just a little bit better of a fit, but not by much. But they asked for the exponential regression model. So remember, we're going to type that in, and we're going to say the a times the b raised to x. So when we're looking at this example, we're going to be looking at substituting in my we're going to be looking at substituting in our A value for A and our B value for B. And it's just that simple. So we're going to say y equals 180.377 times 0.954 raised to x. Now, they may or may not potentially ask you the meaning behind these. So if you remember, the A value is the initial value. So if we're talking about the initial value, we're talking about the temperature. So the A value means that the initial temperature of the cup when it was set on the counter was 180 degrees. Okay, now the B value is my base. If we can see that it's cooling because it's decay, so we can say it's decaying or cooling, and we would need to find the original percentage. Now, if you remember when we did this earlier, we take the original percentage, we multiply it by 100, and you get 95.4%. So then we're going to say 100% minus that 95.4%, and that's going to give us 4.6%. So it's decaying by 4.6%, and it said every 10 minutes. Or wait, it's cooling by 4.6% every minute. So you can always interpret these as well, just by using the y-intercept and then finding the initial value and thinking about it in terms of what they're asking. All right, so number 2, it says a population of single-celled organisms was grown in a petri dish over 16 hours. The number of organisms at a given time is recorded in the table. So in this situation, it says determine the exponential regression equation. Again, that's the best fit. Use the equation to predict. So we're going to be making a prediction, and we're going to round it to the nearest whole number, and they want us to predict the 18th hour. So again, we first need to find that prediction model. So I'm going to go back over here, and you would put in a new table. You would delete what you already have. You would put in a new table, delete that, and then hit and then table, and then start typing in that information. Now again, I've already typed this in to save time. So I've hit that zoom. You can kind of see it's got that curve right there. So it does have like an exponential look to it. So we're going to type in our y1 squiggle A times B, and we're going to raise that to x1. And don't forget to hit that log mode. We can see that it has a correlation coefficient of 0.99, which is a really good fit. So we have our A value is 27.203. And then our base, our B value is 1.151. So we are seeing some growth here. So again, if we were to say this, we would say A, there was initially would say about 27 bacteria in the petri dish. And then my base, we would be saying it's growing because the bacteria is, or the base is greater than 1, so it shows it's growing. And it's a growth by what? So again, we would say 1.15. We'll just leave it at that. Multiply it by 100. And that gives me 115%. Subtract 100. And we would get 15%. So it's growth by 15. And it says it looks like it's going every hour. So about 15% every hour that this bacteria is growing. But again, they want us to make a prediction. So we need to actually write our best fit model. So we're going to say y equals A was 27.203 times my base is 1.151, and we're going to raise that to x. Now, this is where the prediction comes in. We need to make a prediction, And that prediction, we're going to substitute in for x. So the 18th hour, hours is the x value. So we know we're going to substitute that in for x. And once we do that, it's going to help us to make a prediction about how many bacteria in this petri dish on the 18th hour. So we got 1.151, and then we're going to raise that to 18. Now, once you have that put in, you can type this in. You can say 27.203 times 1.151. And we're going to raise that to 18. So we get approximately, our output value would be approximately, it did say round to the nearest whole number, so 342 bacteria. Now, another way that you can use Desmos in this situation is once you have the equation, we know that x equals 18. Type in x equals 18 and go find that intersection. And we see that it's going to be the same number that we got just a second ago, the 341.2. So we would round that. And then give and take up or down just depending on how you round. Okay? All right, so for the next one, it says the accompanying table shows the amount of water vapor Y that will saturate 1 cubic meter of air in different temperatures. So depending on the temperature, depends on how much water is being evaporated. So they want us to write an exponential regression equation, and then they want us to predict how much water will be saturated, that will be saturated at a temperature of 50 degrees Celsius. So, again, we need to write our best fit equation. And we're going to put this into Desmos just like we did previously. I went ahead and put that table in. But again, you would just go to the plus sign, put the table in. Again, I can see that that does have that little J shape, so it is showing an exponential model. So y1, A times B. And we're going to raise that to x1. I forgot my squiggle, so let me go back. There we go. Hit the log mode. And I'm able to say that my A is 4.194, and my base is 0.068. And again, we could go and say that, our initial value would be like how much we're comparing for the water vapor initially, be like 4.194. It's kind of, that would just be the initial value. I can't necessarily say that would be initially because we are going into the negative this time. We normally don't go into the negative, but because we are going into the negative, it's kind of hard to say that's the initial value. All right, so then, of course, my base, if I were to ask for the rate, I'd multiply that by 100. And I would be able to subtract that and then get my fact that I'm growing. So my vapor is evaporating more over time. So here's my model. And again, they want us to make a prediction for 50 degrees Celsius. So we're going to plug that in for X. So 4.194 times 1.068. And we're going to raise that to 50. So we can put that into Desmos. And we're going to say 1.068 and raise that to 50. And so we get that the approximate water vapor evaporation would be 112, we'll say 0.5, and that's going to be in grams of the water evaporation at a 50 degrees Celsius. Now, we know that X is, if we're using Desmos, we know that X is equal to 50. So if I kind of come back, let's try that again and put equal 50. So if I were to come back to my graph, go over to 50, and I could see that they get about 110.2. And again, it's all about how I rounded that kind of made mine a little bit more, but that obviously the 110.2 is a more accurate answer with my give or take. All right. And then this last one, I do believe I've seen this on a check-in at some point, but it says the table below shows value of a computer as a fraction of time elapsed as it was manufactured. So it says the value of the computer decreased exponentially through a 5-year time period. What is the average decrease over the years t equals 2 and t equals 4? Well, if you notice in this table, we got 1, 3, and 5, but we're missing the 2 and we're missing the 4. We're missing those values. So we need to figure out what that is in order to find the annual amount of decrease. So the annual amount of decrease is going to be my rate of change between those two. So we've done rate of change. We should know how to do rate of change, and we should know that it's y2 minus y1 over x2 minus x1. But I cannot do my rate of change just because I don't know my values of 2 and I don't know my values for 4. So we're missing those values in there. But what I can do is I can find my exponential best fit model and find the values of 2 and 4. So that's basically what we're looking at right now, is we're going to find our best fit model, and that's going to help us find my y values for that situation. So I'm going to go back. I've already got my table put in. I can see it right here. I almost could probably eyeball it, depending on how it's, shaped, but I'm going to go ahead and put this in. So y1 squiggle a times b raised to x1. And I'm going to click that log button, and I get that my best fit model is y equals 800 times 0.5 raised to x. So what this is telling me is it's telling me that I'm multiplying by 0.5. So what I'm going to do is I'm going to kind of show you a few different ways. So if I know I'm going to 2, I would say times 0.5. So if I multiply by 0.5, half of 400 should be 200. So then I could do it again, and then I'd multiply that by 0.5, and then half of 100, if I do it one more time, half of 100 would be 50. And I could actually find those values. Or I could use my graph to my advantage, and I can say, okay, I know I'm looking for the x value of 200, and I'm going to go ahead and look at that x value, and I'm going to scroll out. Now, note, not 200, I'm sorry, the x value of 2. I was like, why is this not working? All right, so if I go to x value of 2, find that intersection, I may have to do quite a bit of scrolling to help me find it, but I can find it that it is 200. So we now know that that's 200, and then I can do the same thing with the 4. And if I do the same thing with the 4, of course I'd have to do a little bit of scrolling, but I can see that that's 50. So however you choose to get your values, just understand that you have to find the best fit model first, and then realize that you're multiplying by 2 each time. So if we're multiplying by 0.5 each time, which of course is half, and if we're going by half, that means we're splitting it in half. Technically it's times 1/2 or divided by 2. So I should be able to see that we're dividing by 2 each time, or multiplying by 0.5 or 1/2, however you want to say it. But now that we have that, we're going to calculate our rate of change. So they want us to find the rate of change between those two values. So if I'm calculating the rate of change, my y2 is going to be 50 minus my y1 is 200 divided by my 4 minus my 2. So again, when I'm looking at that, I have 50 minus 200 is negative 150. And then negative 150 divided by 2 is technically negative 75. Or type it into Desmos like you're used to doing. You've done it 1,000 times before. Do that little fraction sign and then do 50 minus 200 and then 4 minus 2. And you get negative. Now, here's the thing. In the problem, it said give the answer as a positive value. So, yes, we know it's decreasing, and we're going to put 75 as my final answer and drop the negative. All right, so just with exponential, you're basically doing the exact same thing you were doing with linear. The only difference is instead of putting in the linear formula, you're now going to put in the exponential formula.